Okay, welcome to today's webinar um, about simulating flooding in coastal areas by the actions of sea level rise, storm surges, and tsunamis. Um, I want to share with you the motivation for this webinar. We actually um, have been getting a lot of requests or questions about the capabilities of the river flow 2D model to simulate coastal flooding. And that's partially because the name of the model is river flow, and people associate that directly with rivers. However, um, one of the purposes of this webinar is to demonstrate that the river flow 2D model is actually a shallow water equation model that is able to handle coastal flooding with the same accuracy that it can handle riverine and floodplain flooding. So that's mainly the motivation, the initial motivation of the webinar. So I'm going to center the discussion today about three different sources of coastal flooding. They are not the only ones, but they are very important ones. And they are the sea level rise, storm surges, and tsunamis. I will also talk about the tools specific to coastal flooding that are available in river flow 2D model. And I will share with you also some animations and some applications of the river flow 2D model for coastal flooding, mainly the Sandy hurricane flooding in Manhattan that occurred a couple of years ago, but also other applications, and some of them have been provided by users and clients that we have. I will also have the chance to answer any questions you have, and probably I will let this to the end. So feel free to use the question and answer panel on your GoToWebinar control panel. And at the end, I will read the questions and I will try to answer as many as I can. Okay, so there are several sources of flooding in coastal areas, and most of the time they are not isolated. They act in combined form. So I borrowed this from a book, and this shows most of the main factors that influence coastal flooding. So we have the mean sea level here. There may be some oscillations related to, in this particular case, related to Florida. In Florida, there is an influence of the El Nino event for coastal flooding, and that has a very an impact on the sea level that is occurs every few years. There is also the tidal range, and also storm surge that is occasional. It occurs only when we have a hurricane or a tropical storm. Obviously, the waves have an influence, and they all finally can have an impact on the coastal area here. So the combination of these factors may affect how the coastal area is getting flooded at some point. So I'm trying to discuss each one of them separately. So first, sea level rise. Now, sea level rise is, I'm not getting into why it's happening. It's just a fact that it's happening in many parts of the world. It's been measured. It's been demonstrated. So it is a fact that is already impacting several areas. And what are the main impacts on coastal areas in particular? Well, first, they can generate more inundation, not only of coastal areas, but also in inland areas that can be affected or can be sometimes connected by rivers or canals. It's also another factor that it gets combined that increases the frequency of flooding in coastal areas. So the higher the sea level and the combined effect of with storm surges and tidal effects, that generates coastal flooding. It happens that I have a meeting a couple of weeks ago, a friend's house near the coast in Florida, and he's been living there for 25 years, and he's already getting flooding out of tidal, the maximum tides in his house, and that's remarkable because it doesn't need to. You don't need to have a high storm surge or hurricane or things like that. It's just the tidal influence combined with the sea level rise that is causing these effects. As I said before, the increase of flooding in interior areas affect storm water infrastructure. Then you have other effects that are not related necessarily with flooding, but they generate some impacts also. For example, salt water intrusion in aquifer. If some areas that depend on wells for water need to abandon some wells because of salt water intrusion. And there is a lot of issues related to contamination, pollution of the transport of pollutants in coastal areas as well due to flooding. There are other impacts, socioeconomic impacts, displacing of people that need to move out of areas that were available before for urban development, the decrease in property values, increase in insurance costs. All these effects are secondary, not directly related to or only related to sea level rise, but they are also very important. As I said before, also the sea level rise is a fact. It's not something that is only a prediction. It's something occurring already. And these graphs, I think, that demonstrate that at least in the last 20 years or so, there have been not only an increase in the sea level, but also an increase in the rate of change of the sea level. So in the last maybe 5 years or so, there have been some acceleration in this rate of increase that is exacerbating the problem in some areas. Now, this graph is very important. First of all, it's a measurement, and this is in Virginia Key in South Florida. And you see here this extreme events that correspond to hurricanes most of the time. You see hurricanes Wilma, Irene. These events, which are not related to hurricanes, are also very important and are related to tides. So the combination of factors is a big issue here. And that's something that happened in Sandy, where the high tide was combined with the maximum storm surge and also a relatively high sea level that's been happening there too. So all these factors need to be understood and taken into account when we want to assess mitigation measures or adaptation measures for the coastal areas. So the previous slide was measured. There are no projections there. But there have been projections. There are projections that are being done and followed in order to plan mitigation measures for coastal flooding in particular. And these are this slide here shows a figure for the present projections that are available for South Florida. And as you see here, there is a big variation in different projections by different agencies, but all of them essentially predict a big change and also an acceleration in the sea level rise. So this sea levels predictions are being used for planning purposes in many parts of the world. But again, I want to remind you that there is not a single factor. There is always a combination of factors, either sea level rise plus tides or sea level rise plus a storm surge, etc., that causes the flooding problems. In particular, the storm surges are well known in different areas because they occur for a relatively short period of time, but they create a lot of problems. And they're mainly generated by tropical storms, even subtropical storms as well, hurricanes and so forth. And these graphs here, taken from the USGS website, illustrate how they can affect coastal areas. Again, you have combinations of factors. You have a river maybe coming into an area. You may have barrier islands. And when you have a storm, that storm creates some pressure on the sea. And in addition to the waves, it elevates the level of the sea. And that in combination with wind waves creates the flood surge that can flood these areas that may be populated and also more inland areas. Now, what happens is that usually when you have the storm, you have also rainfall. So you have the effect of the rainfall in addition to the storm. So the inundation problems is also exaggerated sometimes. Now, all of these events create a big challenge for computer models. There's a number of them. I'm just discussing a few of them that I think are very important. First, that the models need to correctly and accurately represent the urban environment. They need to be able to capture buildings, streets, different features that you have in the urban area, and the approximation that you make with the model needs to be able to resolve the terrain. And also, since the flooding is not constant, occurs during a certain period of time, there will be some areas that are wet, some areas that are dry after, and the model needs to account for that accurately. The model needs to also resolve the structures like levees, walls, roads, many different structures that affect how the flooding occurs in the urban environment. So the approximation, the numerical approximation that you make with the model needs to be able to capture the geometry and adapt the mesh to that geometry that can be arbitrary because they're not straight lines normally. Also, to simulate flooding in urban areas, you normally have multiple inflow and outflow boundaries, and water may leave sometimes, get out of the mesh, sometimes is entering the mesh, and the data should include not only discharges from rivers, but also stages from tidal records or storm surges or tsunamis or whatever the factor is. So there is a combination of boundary conditions that need to be taken into account. And also, since the storm can occur first on the sea and then on the inland area, the model sometimes need to account for the rainfall in addition to the storm surge or the tidal influence downstream. So all of these represent challenges to models because the models need to be able to represent these features correctly. Now, the river flow 2D model, regardless of the name, again, that is a river, is not only applicable to rivers, it's also applicable to coastal areas and urban coastal areas as well. Because it's a general purpose shallow water equation model that solves the full equations that are applicable not only to riverine environments, but also to floodplains and also coastal environments. And it is a combined hydrologic and hydraulic model, so it can simulate simultaneously the rainfall event and the hydraulic routing of the flooding. I would suggest that the main characteristics of the river flow 2D model is that it's based on flexible non-structured mesh. I will talk about this and why it's so important for flooding of coastal areas. It has a robust wetting and drying bed algorithm that accounts for the drying of the area when you have no more flooding. The numerical engine is very fast, accurate, and very stable. It can handle hydraulic structures in 2 dimensions. I will talk a little bit about this too. It's integrated with the SMS GUI. I will also talk about the InfraWorks, Autodesk InfraWorks project Boulder today, because there are some examples I want to show you about this exciting new beta version. And the model has a GPU model that runs much faster than the non-parallelized model. So this GPU model is really important in accelerating simulations when you're doing a lot of scenario analysis. Now, all of this is done by Hadronia in collaboration with our partners at the Computational Hydraulics Group at the University of Zaragoza in Spain. We have a very active collaboration with this group. And also, we have a partner company in Spain that is Hadronia Europe that handles our business in that part of the world mainly. And we have recently received a funding for a collaboration with the university by which a PhD student is working on further development some components of and some improvements to the numerical performance of the river flow 2D model. Now, the main numerical properties of river flow 2D that are important for coastal and riverine environments is the accuracy. The model ensures accuracy regardless of the flow regime, low velocities or high velocities, wet, dry areas, bed gradients, and depth, without any adjustment. So you don't need to be tweaking things to make that your results accurate. Numerical solution is not sensitive to obscure parameters or even numerical parameters such as the current number. And there are dozens of numerical tests and hundreds of projects that demonstrate that the model is always numerically stable and consistent, providing realistic results for real projects. So again, the flexible mesh, what it is just a mesh form of triangles. And these triangles can vary in size. And you can develop the mesh in such a way that the mesh is adapted to any building or street or whatever obstacle you have in your urban area. You can have a zone wall, you can have a coastal wall, you can have define the elevations of that wall that can vary along that. And you can do that exactly because the mesh does not approximate that polyline. It's just exactly create elements around that structure. Also, the velocities can vary in any direction. It's a full two-dimensional model, So you're not restricted to any specific directions on the velocity that you can have. The mesh generation, again, you can have a refinement, so you can add a lot of detail in some areas where you need more uh, accuracy. That allows you to capture exactly the topography, and also to represent buildings, street levees, and walls, as you can see on the right image here. So if you have buildings and things that obstruct the flow, as you can see here in this riverine environment, you have two houses that affect how the flow is occurring. So you can go to just the simple prediction of stages, but you can also get a lot of detail on how the model is predicting the velocities and velocity patterns on the area. Now, in regards to the particularities of the boundary conditions that are required for estuary and coastal flooding simulations, in case of the sea boundary or coastal boundary, normally what you need there is the stage versus time or free outflow, and normally you have tidal records, storm surges, or tsunamis. They all are represented by stage or water surface elevation versus time. So there is a specific boundary condition for this in river flow 2D. Just set the time history is just a table of stages versus discharge, and the model automatically will determine the flow out of the mesh through that boundary. But you can have also that boundary works seamlessly for inflow, so you don't need special things to do on that particular boundary. For riverine inflows or some other kind of inflows, you normally have discharge versus time, and in that case you have to provide the inflow hydrograph, so it's a variation of discharge versus time. These are only a couple of the available boundary conditions are available, but in bottom line here is that you have all the boundary condition types that you normally use in the coastal environment or the estuarine environment. As an example, I'm showing here the area of Manhattan, and you have the Hudson River, and also the area that is close to the sea here. So typically, if you wanted to use river flow 2D in this environment, you would discretize this whole area with a mesh, and you would have conditions, boundary conditions where the mesh ends. Maybe you will have a variation of discharge versus time from the Hudson River. You may have a free condition in the what is called the East River here, and you normally will have a water surface elevation versus time in this boundary here that, as I said, can be inflow boundary or outflow boundary depending on the dynamics of the flow inside. So it's automatically accounted for in the model whether this is an inflow or an outflow boundary as a function of the water elevation time history that you provide there. So this water elevation versus time can be any water elevation. Can be a tsunami, it can be a tidal record, it can be a storm surge, it can be any variation of water elevation versus time that you need to do to create a scenario for flooding in this area. It's very simple to select the boundary conditions using the SMS user interface. Also with the InfraWorks project Boulder, you're able to use that type of selection method. Is similar, but you select the inflow or outflow boundary, and you select what type of condition you want there. In this case, we are selecting a free inflow or outflow that lets flow in and out without necessarily giving a stage there. You can also enter a water surface elevation on different boundaries, and create a table. This is a very simple triangular variation of the water surface elevation versus time, but you can enter any table of any length as well. With the data input program, you have also tools to select, and this is a new a panel that we have added, where you can select the boundary specific boundary condition, look at the graph. You can change the tables here or import different tables and just perform the simulation without having to recreate a mesh or going back to the spatial parameters that you need in SMS. Other components for coastal flood assessment, sorry. Culverts, you can have culverts, weirs in 2D, bridges, gates, and especially variable roughness with depth. This is useful sometimes for vegetated areas and coastal areas that sometimes have vegetation that can improve the resilience of the area to flooding. The bridge component is a very comprehensive two-dimensional bridge component that computes the energy losses on virtually any geometry bridge. Sorry about that. And as I said, it's a two-dimensional component. So you define, like you can see here, a polyline, and that polyline represents the bridge alignment. And then you have a way to graphically create a bridge geometry or import a bridge geometry file that represents the form of the bridge cross-section, including the deck. Now, I think that the model has a unique feature that allows to simulate both pressure flow and overtopping of this kind of structures. And this is very useful for coastal areas because sometimes in estuary conditions, you have the downstream water elevation creates a backwater effects that affects also the performance of the bridges that sometimes can flow under pressure or even get overtopped. We have also the hydrologic component that you can just use in addition or in combination with the hydraulic component, and it handles distributed rainfall, evaporation, and also distributed infiltration. There are a lot of tools for dynamic visualization, and what I've been talking up to now, it's related to the SMS user interface. But you have ways to generate Google Earth files that can be shared with clients and colleagues. So let me now talk a little bit about some examples that I would like to share with you in regards to applications of the river flow 2D model. The first, let me show you a tsunami wave simulation. And a tsunami, as you know, is a solitary wave, so it's a single wave usually, or a couple of waves at most, and they are extremely important because they can generate catastrophic effects on coastal areas. Now, the purpose of this simulation is mainly to validate the model and demonstrate how the model can accurately reproduce measured results corresponding to tsunami. So the idea is to compare the model results with run-up data. And this example corresponds to an actual event, of tsunami event that occurred in 1993 in Japan. And in this event, there was a measurement of the high water marks that occurred on that island. But more importantly, there was an effort to recreate the event using a scale lab experiment. And this was done also in Japan in a large scale tank. Is 200 meter long tank. So it's a massive a tank, very almost. It's not obviously a natural scale, but it's a quite a big scale for this type of analysis, 1 in 400. Uh, but the interesting part here is that the model was applied to this geometry and to compare the measurements with the model results. And in this example, what it was done is to try to replicate the event that occurred in Japan by imposing a boundary condition here. What you see here is the bathymetry. And there are 3 locations where the experimenters measured the water elevation here, 0.5, 7, and 9. And so the bathymetry looks like this. So you have a very deep, relatively deep water here. You have the coastal area here. And these are the 3 points where the model is compared with the data. This is the boundary condition. So this is the water level variation at the sea boundary. And these are some results. So let me explain to you what these results mean. You see here 3 graphs on the, or 4 graphs on the bottom. This is the actual boundary condition that is being imposed in this part of the domain. This is the comparison of the model, is the black line, and the measured values in the flume experiment are these dots, the blue dots here. So, and these are the 3 points that are located 5, 7, and 9 here. So I will show you different images corresponding to different times. And the arrow on the lower left graph represents the state at which we are in time. So you see at this point, we start measurements. And then you see here how the model behaves. Is very accurate in representing the elevations that occur here, that they are very complex, by the way. You see here all these wavy patterns that occur, and they are all captured very well by the model. So the idea was to understand how the model was able to represent this kind of complex events in reality, but since it's so difficult to get the actual data, it was preferred to use the experimental data to make the comparison. Now let me give you some examples of storm surge applications. This particular one was done by Angel Espinosa. He is at Autodesk, California, and he developed all this model on his own using InfraWorks and RealFlow 2D, which is the what is been named Project Boulder. So Project Boulder is a collaboration between Autodesk and Hydronia, and at this point is on the Autodesk Labs. So you are free to download. This is free until June, and is on experimental state now. So it's being evaluated as a potential final release this year. But so far, at this point, you can download the program, and you will be able to create examples exactly as the one I'm showing now here, that was kindly offered by Angel. And so this is an animation. This is Malibu Beach. So you have the InfraWorks is very efficient in representing the three-dimensional view. Is very realistic. And you have the sea here. It's fully integrated with RealFlow 2D. And let me show you how you can see a simple simulation of a storm surge in this coastal area here. So you get it's very quick running and also representing these animations. But it's very illustrative to look at the actual flooding, and you can see the houses. You can manipulate this in 3D and look at how they behave during the storm surge. This is a different application also provided by Angelo Espinosa at Autodesk. But you have all kinds of tools to create these realistic effects there in addition. But the numerical engine underneath all these simulations is the Riverflow 2D model, the same model that is available as a full version as well. Let me turn now to the Hurricane Sandy flooding simulations. This is a very interesting thing. We have done two things. I'm going to present you some results that was done independently by Stephen Costa at Microsoft Resources. They are Autodesk partner and located in New York. And they developed this tool to illustrate the potential use of the Riverflow 2D model with the InfraWorks. And they have provided all the files that I'm showing today here. So you are also welcome to visit Stephen Costa blog, and they explain in more detail what they did with InfraWorks. And the second thing I'm going to present is the application. We replicated more or less the same thing in SMS, so you can see more or less the differences. So this is an animation created by Stephen on the flooding of Manhattan, lower Manhattan, from the Sandy hurricane. So this is the terrain, what you see there. Let me turn on the animation. So what you see here are the water depth variation in time. And you can see here how these areas are getting flooded as the time progresses. And you can get a lot of detail, as you can see here. And with Riverflow 2D, you can have as much detail as you decide, because you can refine the mesh exactly on the areas that you want without having to create a lot of unnecessary elements elsewhere. So in this particular case, there is a mesh that can capture the streets and the buildings in a lot of detail as well. They are experimenting here, the Microsoft Resources, with different options for mitigation. And in this animation, you can see some of these options that is kind of wall here that can avoid the water from flooding this coastal area. So this is without any, so this would be the existing conditions, and this would be the planned work they design, they want to do here. So as I said, we try to gave a different view using Riverflow 2D within SMS. And in this case, we created this mesh here. What you see here, this black area is not an error, or it's just that the elements are very small and they appear to be uniformly black. But this is the lower Manhattan area where we want to get more detail. So we decided to use a relatively coarse mesh in the Hudson River, the East River, but we wanted to illustrate how you can have more detail just by refining the mesh in the areas that are more sensitive to your study. This is the detail of lower Manhattan. We decided not to include the Brooklyn area or some other areas, just we wanted to focus here. But you can also create a mesh that extends to this area very easily. By the way, we didn't have any data when we started this, so we are using all the data downloaded using SMS tool to download from the web. So all the data that we use to make this simple application that is mainly an illustration of the use of the model for coastal flooding was taken from public sources, is free, and it was all downloaded using the SMS tools that are available for that particular purpose. So we decided to use the GPU version, and we ran 14 hours of the storm surge. It takes about 3 minutes to run the 14 hours. And again, I want to just point out that the volume conservation error of the model is always very small. Typically is of the order of 0 or so. So it's very quick to make an application like this for coastal environments. So again, we are not pretending that we are calibrating or just trying to replicate anything. There was no calibration involved at all here, but I was curious to know how good or bad we were getting the depth or the at least the impacted areas. And I found this map online where it shows in red the Hurricane Sandy flooding areas, and they come pretty close to what we got here, even though we didn't add a lot of detail on the streets or buildings, particularly in this part of the area. But all these areas are being flooded as is predicted, or it was observed with Sandy. So it's pretty close. You see, it's very curious to see this island here. It's almost exact here, and we didn't do any specific things except for taking into account the bathymetry and the elevations that are taken from the web source. Let me show you an animation that we also generated with the model for the simulation. So you see here how the model first predicts the flooding, and then you get the dry areas. And actually, as you saw before, this is resolved by the model. So you have elements here. It's just that they are dry and they get wet just during the storm surge. So some final comments. I want to stress that sea level rise combined with the effect of storm surges and other factors is increasing the flood risk in coastal areas. That's a fact. It's been occurring in many places, and our aim is not to. We don't have anything to do with the causes, but what we can do about it, and what we think at Hydronia at least that we can provide, is a tool by which you can support mitigation measures, or at least the support projects that assess adaptation to evaluate designs that can mitigate flooding in some way. And two-dimensional models are very useful for this purpose because they can provide a lot of detail. And in particular, the river flow 2D model can be applied to urban coastal environments and combine river estuary coastal areas, including hydrology and hydraulics, and study the combined effect also of the sea level rise and surge or tsunamis in this coastal environment. Well, that's essentially all I wanted to share with you today, and I'll be happy to answer some questions. And let me turn to my questions panel. Okay. Let me go one by one. I have many of them. Let's try to do it. Okay, I have a question here that is related to the use of LiDAR data. Any suggestions how to get better flooding results when working with downloaded LiDAR data that does not contain surface data below the waterline? Yeah, that's a big issue because as you know, the LiDAR data ignores what's below the water surface. And when you're solving a riverine problem with LiDAR data, that data assumes that the water surface is flat. And so what you can do in SMS is, for instance, define a polygon that covers all the riverine area, and you can use a different data set on that polygon that covers the river, and then use the LiDAR data set on the floodplain, all the coastal environment. You can also create a data set that is just an assumption. If you don't have any better data, you can assume a certain depth and then create a scattered data set that reduces the bed elevation only on the river, and then you have a new scattered data set for that. There are many tools to do that. I just mentioned two of them. A question: can we edit the flexible mesh in InfraWorks? Well, the idea, presently the existing version that is in beta now uses a uniform size, more or less uniform size triangles. As you saw in SMS, you can have quite a lot of detail and refinement. But in InfraWorks, the present version is only available in that way. But the Autodesk is working on a mesh generation plugin that will allow, hopefully, to refine the mesh automatically, and that mesh will adapt to the different complexities that you may have in the terrain. So that's under development. Okay. I have a question here. Since the solution highly depends on the quality of the mesh, how good is the RiverFlow 2D meshing process? It is automated or is user intensive? Well, we have two options. Now we have InfraWorks that the idea is that it's totally automated. In SMS is partially automated. You can generate a mesh and refine it by giving some guidelines to the mesh generator. And we are also in the process of developing a completely new meshing or adaptation to existing meshing engines that are also automatic. But it's a combination. Sometimes you need to manually add break lines and things like that to improve the mesh. However, the model is not too sensitive to the mesh. So you can have the model will determine if you have very acute elements. I will not let you run with elements that are angles, internal angles less than 5 degrees. But provided that your size, your element forms is relatively well behaved, the model is insensitive to that. I have questions here related to InfraWorks. If you need to reinstall a Hydronia RiverFlow 2D for the new release of InfraWorks, that's a good question. So I don't have an answer for you, but I will take note of that and I will try to answer it later. Okay, let me look at the time now. Okay, I have time for a few more questions here. Okay, let me read it. What happens to your coastal flooding simulation when your base model does not include the entire bay, channels, rivers, or other coastal water area? Will the RiverFlow 2D simulation be accurate if your model does not include the entire boundary of where water might spread? Well, it depends. It depends. It can be or it cannot be. It depends how important is that water body or how much it influences your area of interest. Obviously, if you have if it has a big influence and you're ignoring that in the mesh, that your results will be highly affected by that. However, um, if you select your boundaries carefully and you locate them in and use let's say a adequate tidal record or discharge, the models should not depend too much on where or what's going on outside the mesh area. But it's problem dependent. Actually, it's difficult to give a general answer to that. A follow-up question in regards to this: if the coastal area has a narrow bottleneck, like San Francisco Bay, how would you configure the flow intervals and volume of water coming in from the sea level rise storm surge? Well, actually, the model does what you in the water elevation versus time boundary condition. The user provides the water surface elevation versus time, and the model determines the discharge either out or in. So if you have an estuary condition, you select your tidal record or your storm surge, and the model will calculate the inflow and outflow. You can calibrate the velocities if you have measured velocities to make sure that the discharges are accurate. But the model does not. I mean, you have another condition that imposes the discharge in addition to the water, if you consider that's more adequate. So it's a combined water surface elevation plus discharge. So the model forces to have these both conditions, but that's not the best condition for subcritical flow in estuary conditions. And the model should be able to provide reasonable results for the discharges that are going out or in the mesh in those situations. Okay, I have specific questions here. Let's see. What about wave overtopping in case of dike protections? Well, bear in mind that river flow 2D does not account for short period waves. So the type of waves that occur in some areas, I mean, typically in coastal areas, but the tidal, you need the model accounts for long waves, such as tidal situations or tsunamis or even storm surges. But the model can determine can calculate the overtopping of levees based on the conditions you have. So it is, with that caveat, it's capable of doing that. A question is if we have done any work in the Indian Ocean. Well, not directly hydronia, but I wouldn't be surprised if one of our users can have applied the model somewhere. We have users in all continents, and there may be applications there, but I'm not aware at this point of any specific one. I have a question if the model is open source. No, it's not open source. It's proprietary, and we keep developing the model all the time, and we provide commercial licenses. And for academic institutions, we provide academic or educational licenses that have a significant discount of 50% actually, so half the price of a normal license. Well, I have pricing questions. I will need to refer to you to the website. And the website, you have a store panel, and you can see there all the pricing. Another question here, more technical. Can I define a depth mesh ratio to generate mesh automatically? Yeah, there are ways to do that in SMS. by creating a density map. You can do that. Question on tsunami. Person is curious to know how well the model can predict the arrival time of a tsunami. Well, that's a different thing. What I presented you here is an example of a tsunami that we know or we can estimate in a way the wave at a certain distance from the coast. To predict the arrival time, you would need to model the whole ocean, and I've seen shallow water models doing that, so I haven't seen that particular application for river flow 2D specifically. Oh my God, I have many questions still. Let me see if I have time for a couple of more. Well, I have maybe one or two. Is there a link on the website where you can download reliable surface data? Well, not on the website, but on the SMS system, you have that tool, the one that I presented. You have a web option that you can download from many sources, elevation data. Can you digitize the bathymetry from marine chart under? Yes, you can digitize the contour lines and things like that and create a scatter set out of that and use it as an elevation data set. Well, unfortunately, I ran out of time. I have at least 10 more questions or so, but I regret I need to finish. I exhausted my time here, but I will email you with my answers to your questions as soon as I have a chance. And again, you will receive a link for the recorded webinar and hopefully in less than a couple of hours. I just wanted to thank you for your interest and attendance, and I hope you have found the webinar useful and informative. Thank you.